So our next speaker is Joe Conlon from Oxford University, who's going to talk about dark radiation and the cosmic axion background.
Okay, thank you. So let me start by thanking the organisers for organising this wonderful conference and for giving me the chance to give this talk. So this talk is going to be about dark radiation and the prospect of a 0.1 to 1 keV cosmic axion background and how you would see it. So motivation for and okay, forget that. Okay, so let me start by thanking my collaborators, some of whom are here, and the talk is going to be based on mostly on the 4 papers listed above. There's also a related work which Stephen Angus is going to be talking about this afternoon. Okay, so the structure of the talk. I want to start with just a couple of slides of prelude concerning notation and one complaint about notation. Being a theorist, I then want to start with the theoretical motivation for dark radiation, because I think this is an exceptionally well-motivated extension of lambda CDM. Then want to review the experimental situation, which will have a little bit of overlap with some of the talks on Tuesday by Joe Dunkley and George Stathiou. Then I want to move on to why, if you take string theory seriously, and particularly the existence of moduli in string theory seriously, this suggests that today there should exist a cosmic axion background with energies in the 0.1 to 1 keV region. And then finally I want to say how you would see this and how this may already have been seen through the soft excess in galaxy clusters. Okay, so prelude. Right, so well, one way to kind of orient oneself thinking about this is, we know a lot about what the universe is made up of. From a sort of theorist point of view, you can say, well, we know that most of the non-relativistic stuff in the universe does not belong to the standard model. So we're pretty confident that there exists new non-relativistic species of matter that are not present in the standard model that's probed at the LHC. So then there's also some percentage of relativistic stuff in the universe that does not come from the standard model. So this is where we can't fill it in, but it lies somewhere between 0 and 10. So theoretically, you can say, well, if dark matter exists, if dark non-relativistic stuff exists, what's wrong with dark relativistic stuff? Another question, coming this from a theory point of view, you can say, well, what new non-standard model relativistic species can exist? Okay, so here's the sort of complaint about notation. So I think one thing that is often true in physics is that good notation clarifies the physics, and the converse of this is that bad notation can obscure the physics. And I think, okay, so I know it's conventional that dark radiation is parameterized by NF, and this is just built into how constraints are done. And what NF stands for is the effective number of neutrino species. But this is kind of misleading, and this word neutrino is highly misleading, because it then leads you to start thinking that what's being constrained or what you're looking for is sort of non-standard neutrinos or new physics in the neutrino sector, when really this has got nothing necessarily whatsoever to do with neutrinos. I mean, what is being probed is additional hidden radiation that is decoupled from the sort of standard model plasma, but this has no necessary connection to neutrinos. And so just again as review, then what NF is basically the total radiation content in the universe, so at C and B times, how this is related to the amount of energy density in photons. The canonical value is 3.046, and so deviations from this are measured by delta NF, which is saying the difference between this and 3.046. Okay, so now I want to give theory motivation for dark radiation. Okay, so the standard picture of cosmology that we all know and love looks something like this. You assume you started with inflation, a period of inflation, very rapid accelerated expansion of the universe. And the inflaton ended, so inflation ended, oscillations about the state. You have lots of inflaton quanta, the inflaton quanta decay, they decay to quarks and leptons. This turns into the hot Big Bang. The hot Big Bang cools down, and then this is what is left of the hot Big Bang today, as has been beautifully observed by Kobe, WMAP, and now Planck. Okay, so what's the sort of twiddle on this you need to do to get dark radiation? Well, it's not really very much. So the inflaton, what is the inflaton? Well, we haven't got a clue what the inflaton is. almost certainly not part of the standard model. No one really has any sort of real idea what this field is. So what you need to do to get dark radiation is, instead of this field decaying just to standard model degrees of freedom, all you need is that when it decays, it also decays addition to a massless, hidden, weakly interacting sector, for example, axions. And if it does this, then this stuff will free stream to the present day, and this will have survived as dark radiation. So this is what's theoretically needed to generate dark radiation, and it's not complicated physics at all. All it is that when reheating occurs, you don't decay 100% of the standard model, you also have decay modes to a massless hidden sector. So dark radiation will occur whenever reheating involves decays to just an invisible, weakly interacting, massless hidden sector in addition to the standard model. And as we heard, particularly in the talk by Andreas Ringwald, such massless hidden sectors exist in many, many beyond the standard model constructions. So the best motivated of all of these is the QCD axion, which you can say most probably does exist. It's an example of something which is essentially massless and very weakly interacting with the standard model. More generally, you have axion-like particles. You can have hidden photons, so additional U1 gauge groups. These very often occur in string compactifications. General wisps, chiral fermions. So if you had like neutrino-like particles from a hidden sector, so basically massless hidden sector particles are well motivated in beyond the standard model constructions and also well motivated in string theory. So what this then tells us is that we should not view such additional massless hidden sectors as kind of particularly exotic physics. And how should we think about this? Should we think about dark radiation? Well, I think the natural way to think about dark radiation is as long as you decay to such a sector, you get dark radiation. Now, I remember Cliff advertised me as a kind of doing hardcore string theory. So here's some hardcore string theory maths. So in the early universe, non-relativistic matter redshifts as a to the minus 3. Radiation redshifts as a to the minus 4. So the hardcore maths is that 4 is bigger than 3. Now this hardcore maths has got a serious point to it, which is that often you have this kind of simplified picture where you talk about there's an inflation, there's an inflaton, the inflaton decays, reheating, hot Big Bang. However, the point of this is that if you've got any non-relativistic matter, stuff that decays, once it's decayed, it goes to radiation, and radiation redshifts rapidly. It goes off as a to the minus 4. If you've got any matter that's non-relativistic, it's going as a to the minus 3. And because A is getting very, very, very big, this stuff wins. So the serious point of this, which is I think not really as appreciated as well as it should be, is that reheating in the early universe is dominated by the last scalar to decay and not the first one. So it doesn't matter if you've got some admixture of the standard model Higgs in the inflaton, which decays instantaneously to bottom quarks. If you've got stuff that is long-lived there, that's just going to carry on redshifting, and it's going to win over all the radiation. And what's going to matter when you analyse the hot Big Bang is the last guy to decay, not the first. Okay, so what is the last guy to decay? Okay, so in string theory, we know there are sort of extra dimensions, and these extra dimensions are parameterized by size and shape by sizes and shape, which are normally called moduli. So often the size modulus, or the size moduli, or the shape moduli. And these are typically massive scalars, and they interact only via gravitational interactions. It means all their interactions are suppressed by 1 over m Planck. Why is this? Well, the easiest way to think of it, often these are higher dimensional modes of the graviton. So because they're basically modes of the graviton, they interact with 1 over m Planck suppressed couplings. And moduli are generically displaced from their final minimum during inflation. So as long as they don't generally in the early universe, the moduli generally don't have a sort of a notion of zero VEV. They're normally away from their minimum during inflation, and so then they subsequently oscillate as 1 over a cubed before they eventually decay. And the important point about moduli is this 1 over m Planck. This 1 over m Planck factor means that moduli live for a very, very long time. So if you think in terms of the 4 forces we know, electromagnetism, strong force, weak force, gravitation, stuff that can decay via the strong force decays very rapidly. Stuff that decays via the weak force takes a longer time. If you've got stuff that can only decay via the gravitational force, and in string theory models you generally do, then almost inevitably they are going to come to dominate the energy density of the universe, and reheating is going to be driven by the decays of these fields. So one thing I would advertise as what I would say is a generic expectation of string compactifications is that the universe will pass through a stage where it is modulus dominated. So the energy density is dominated by non-relativistic, massive moduli with gravitational couplings, and reheating will be driven by the decays of these moduli. And so then, coming back to dark radiation, you then expect, if you expect reheating is driven by modulus decays, the part that goes to the standard model gives the hot Big Bang. Any hidden sector decay modes, for example, to axions, will give you dark radiation. And so, this is an ideal subject for string phenomenology, because what this is then coming down to is what are the couplings and the decay modes of moduli, of Planck-coupled particles. And what you would say is that if stuff is Planck-coupled, you would generally expect gravity talks to everything. You expect moduli to couple to everything. In the visible sector, you would couple to, for example, SU3 gauge groups, Higgs fields, and so on. The hidden sector, you can couple to axions, hidden photons, all with Planck-suppressed couplings. All these couplings involve factors of 1 over m Planck. They're all roughly the same size. So you expect to have non-zero decay modes to such hidden sectors, and this is supported by explicit studies of string compactifications and string effective field theories. And the upshot is that, if you think that the world is really, string theory is going to be correct and the world really is 10-dimensional, then you expect moduli to have axionic decay modes, and with a natural branching ratio lying somewhere between 1% and dominant. So from my point of view, this is this is why one should take dark radiation seriously. All that you need for it, it's not complicated physics. All that you need is that when reheating occurs, whatever does decays and does reheating, it's got some branching ratio to hidden massless particles, for example, axions, and such decay modes are in fact generic in well-motivated theories beyond the standard model and string theory. Okay, so just to put some numbers, so I'm assuming a reheating temperature of around 1 GeV, which corresponds to a modulus mass of around 10 to the 6 GeV, then the actual magnitude of delta NF is given by basically 3.4 times the hidden sector branching ratio divided by 1 over 1 minus that. So, for example, if you're going to have delta NF as 0.5, essentially this means that what you're probing is roughly a 15% branching ratio to hidden sectors. So, given if you say that delta NF can't be any bigger, say, than about, you say like 0.7 or 0.8, then roughly what you're saying is that at reheating, your hidden sector branching ratios are bounded to be below about 20%. So there's quite a lot of room to have the inflaton, or whichever last particle to decay, going to hidden sectors. Okay, so now, being a theorist, I started with the theoretical motivation. So I now want to just sort of summarize the experimental situation. Okay, so delta and F can be probed by both the C and B and through measurements of primordial BBN abundances. The reason why is delta and F changes the expansion rate. So because it changes the expansion, for example, in BBN, extra radiation changes the expansion rate as a function of temperature and therefore affects the resulting abundances. In the C and B, delta and F modifies the damping tail, and so you can be probed by the ratio between the damping scale and the sound horizon. And these affect, so for example, the primordial abundances, and in the C and B, this affects the shape of the spectrum. And so recent observations have tended to hint at levels somewhere between 1 and 3 sigma for delta and F bigger than 0. So, some of these measurements appeared by the talks in Joe Dunkley and George Statue. So, I mean, it's good to, I think, split these into measurements which include the Hubble constant and don't include the Hubble constant. So one also comment here is that sometimes it's said that, before Planck, there was sort of evidence for dark radiation, and then after Planck, this had gone away. I think it's more accurate to sort of, it's more accurate, to compare like with like, because, to basically compare measurements, look at measurements without the Hubble constant, combining with the Hubble constant, and with measurements combining with direct measurements of the Hubble constant. And you see that the situation is, broadly the same, before and after Planck. If you combine with the Hubble constant, you have, you are an interesting amount above 3.046. If you don't combine with the Hubble constant, before and after Planck, you are roughly kind of within 1 sigma of it. So anyway, so these are all numbers that have appeared within the last eight months or so, and you see, there's a tendency to be high, and particularly when combining with the direct measurements of the Hubble constant in the local universe. So this was discussed earlier. So just to so the Planck fit to lambda CDM makes a prediction for the value of the Hubble constant in the local universe. Again, it's important that this is a prediction; it's not a measurement, so it must be tested directly by observations. And the prediction is 2.5 sigma discrepant from the direct measurements of Hubble, not the Hubble constant. So one thing I want to also, so this is one thing I've tried to find out about, but I haven't been able to find anyone to give me an informed opinion. So there's this recent paper from June which quotes a value of 76.0 plus or minus 1.9. Now it's all about kind of models for Cepheids and convective pulsation models and stuff that I don't really know anything about. So I'd be grateful if someone can give me kind of an informed opinion of what to think about this paper. Because obviously this is, while consistent with the direct things, this is very substantially high compared to this. So but it's got a question mark because I haven't really had an informed opinion on it. Okay, and the point of the difference of the Hubble constant is that the tension can be relieved by increasing delta and F, as an increase in the Hubble constant is degenerate with an increase in delta and F. Okay, so an independent probe of NF is via BBN. And so last month there have been new determinations of the primordial helium abundance and the primordial deuterium abundance, appeared both within the last month. So the values quoted for helium are here, and the one for deuterium, which has appeared here. So these are definitely shrunk compared to the previous ones. So the updated bounds for the deuterium abundance combined with the C and B is now roughly 1 sigma high, and so this updates a previous value from the Planck paper from March. And interestingly enough, in this paper there's also quoted a pure BBN value for delta and F, which is something like 2.9 sigma high compared to 3.046. And the thing to emphasize about this, so this value is, so wherever you think about the C and B measurements or Hubble constant measurements, this in principle is completely independent of those. So it's interesting. And this is the plot from this paper of last month, showing, so the blue line is the deuterium abundance, the green line is the helium abundance, and the red line is the combination. So this is a BBN only measure plot, and the result this gives is 3.57 plus or minus 0.18. Okay, so summarize this. Okay, so as I said, I think that delta and F is something which is very well motivated theoretically. And so it's interesting that all the kind of determinations of NF have come in high, although one has to say there is not decisive significance of any of these. And there's two kind of independent channels, which is the C and B combined with direct measurements of H0 and primordial abundances. Both hint for delta and F being non-zero at a level somewhere between 2 and 3 sigma. Both are sort of consistent with a central value of roughly 0.5. This isn't evidence, that's 3 sigma, let alone being a discovery, but what they are is at least kind of consistent hints for a very well-motivated extension of lambda CDM. And a reason why this is exciting to work on is that this is something that there are many improvements from many different directions. Once the Planck polarization data will improve this, the direct Hubble constant measurements are going to be improved. The primordial abundances, for example, one of the uncertainties in deuterium is low-energy nuclear scattering experiments. So this is something that can be improved from many different directions which are completely uncorrelated with each other. Okay, so I now want to move on to a more specific topic, which is the idea that there's right now, a cosmic axion background. Okay, so this comes back to the idea that the last, in string theory you expect the last particles to decay are Planck-coupled particles because they exist, and if you only interact via the gravitational force, then you live longer than anything which can decay via, say, gauge interactions. And so you expect moduli to dominate reheating, and you expect moduli to have a branching ratio to, for example, axions, and therefore you expect dark radiation from hidden sector decays of moduli. And a point I also want to make about this is that this is pretty much independent of the actual SUSY breaking scale. So whether SUSY should have been accessible to the LHC, or whether it would have been at an energy of 10 TeV or 1,000 TeV, the physics of this is still holds. Moduli are the last guys to decay. Moduli have a branching ratio to axions. Axions are dark radiation, and they free stream to the current day. Okay, now here's where things start to get interesting. Okay, so the decay mode of the decay rate of moduli is basically set by dimensional analysis. You put a 1 over m Planck squared here. This quantity has to have dimensions of mass, so you put the cube power of the modulus mass here. And this tells you that the reheat temperature when a modulus decays goes as the 3/2 power of the modulus mass divided by the square root of the Planck mass. And if you evaluate it, so this gives you a temperature of roughly 1 GeV for a 10 to the 6 GeV modulus, scaling as the 3/2 power of the modulus mass. A modulus can also have direct two-body decays to axions. So if it decays directly two-body to axions, then the energy that the axions have is just that of the modulus mass divided by 2. It's just a direct, simple two-body decay. No complications.
Wait a minute, a scalar decaying to 2 scalars?
A heavy scalar decaying to 2 massless scalars, yes. Yes.
Is it possible?
Yes, it is. Yes, it is. It's possible. Yes, it's possible. Okay, now the energy of such an axion is for if the modulus mass is around about 10 to the 6 GeV, then the axion energy would be around 10 to the 5 GeV. But the kind of real point, what's kind of interesting here is if you think about, okay, what happens when something like the inflaton or a heavy scalar decays? The part that goes to the visible sector thermalizes. Everything rapidly interacts and it thermalizes. The part that goes to dark radiation, by definition of the fact it's dark radiation and it's non-interacting or very weakly interacting, it free streams. It doesn't interact, and because it doesn't interact, it only loses its energy via redshifting. So what's the significance of this? Okay, the decays which thermalize go to photons, and you have a hot Big Bang starting at this temperature. The axions never thermalize, so they start at this energy. And as the thermal bath cools into the CMB, the axions also just never thermalize, and they free stream to the present day. And the ratio of their energy to the photon temperature is the Planck scale divided by the modulus mass square rooted. This is a very large number. For typical moduli masses, this is something like 10 to the 6. So what this then says is that if you have a modulus decaying with axions as a hidden sector, the axions, the dark radiation axions they produce today are more energetic than the CMB by a factor of about 10 to the 6. Okay, so this is one of the kind of key points I want to kind of get across in this talk. That just a kind of very sort of simple assumption about the early universe, that decays of Planck-coupled particles are what started off the hot Big Bang, strongly then suggest that you should expect any dark radiation axions or dark radiation hidden sectors to have energies today which are more energetic than the CMB by this factor of Planck scale over modulus mass square rooted. And as moduli masses are often in typical models around, say, 10 to the 6 GeV, this then says that the axion energy should be more energetic than the CMB by a factor of about 1 million. So while you look for the CMB at microwaves, you should look for such axions at energies in the extreme ultraviolet or soft X-rays. So this says that the hot Big Bang looks something like this. You've got the standard thermal plasma, but you've also got this very energetic dark radiation component sitting maybe sort of 6 orders of magnitude higher than the typical energies of the CMB. And so such axions, being axions, I said they just free stream. So they originate at something like a redshift of 10 to the 12, and then they've just free streamed to today. So they'd still be here today. They'd have started off, very, very, very early on in the universe's history, and they'd still be there today. And so this then give you you can say, well, there's a prediction that such a cosmic axion background will exist. The energies which it will have will be in the extreme ultraviolet or soft X-rays, and the typical flux, through your hand, is a roughly around 1 million per square centimetre per second. So the spectral shape they would have looks like this. It's not a thermal shape. It originates from just the fact that moduli decay, but obviously they all don't decay exactly at the same time because it's a random process. And so as you reheat from modulus-dominated to radiation-dominated, this is the resulting spectrum of axion energies that you would get. Okay, so that's a prediction. You've got a cosmic axion background, energy today's extreme ultraviolet or soft X-rays. What's feeding into this is simply the idea that you've got massive particles driving reheating, which are only interacting gravitationally, and they've got a decay mode to hidden massless sectors such as axions. Okay, so now I want to come on to the last part of the talk, which is that if such a cosmic axion background is there, how would you see it? So this relates to what Andreas talked about yesterday. So how do you see axions? So the generic axion Lagrangian, it can involve a coupling to photons, an E dot B coupling to photons. It's suppressed by a scale m, which is somewhere bigger than 10 to the 11 GeV. If you turn on a magnetic field, there's a finite chance for an axion to convert to a photon. And if it converts to a photon, you can see it. Okay, so the precise formulae for the conversion probability, if you go through a domain of size L, is as follows. And the two angles here, so the first angle, so these parameters are going to be typical parameters for either the axion energy or heading through a galaxy cluster. Point to take is that the first angle is always small. You're always in the small angle approximation. The second angle is not. The second angle, you can come out of the small angle approximation. Okay, so if you want to convert axions to photons, well, how do you do it? How do you want to do it? So what you want is a big magnetic field, that's clear, and you also want it to be coherent over a large volume. And this is where galaxy clusters come in. Okay, so there are various frontiers in particle physics. So you have, the LHC represents the high energy frontier. You have other sort of, say, precision experiments that represent, flavor experiments that represent a sort of precision frontier. Well, galaxy clusters also actually sit at a frontier. And they sit at the frontier of large magnetic fields over large volumes. Because you have reasonably large magnetic fields, micro-Gaussian scale. They're coherent over length scales between 1 to 10 kiloparsecs. And I can tell you that as kind of a particle physicist, anytime you get to use an equation where you get to put a kiloparsec in the numerator, it feels fantastic. And these magnetic fields exist over roughly, the typical scale of a cluster is a megaparsec. So these are sort of, there's a big volume here, and so you can actually do something with this. Okay, so I'm going to focus on coma. This is well observed, it's reasonably large, it's nearby, and it's also at high galactic latitude, which is important because soft X-rays are heavily absorbed within the galactic plane. Okay, so this is what coma looks like. That's it in radio, that's it in the visible, and that's it in X-rays. Okay, so the idea is basically axions. Okay, they propagate through the cluster, they'll propagate through coma, they'll feel the magnetic field, they can convert to photons. If they convert to photons, you can see photons. So the energy density, if you have a cosmic axion background, or indeed any dark radiation, the energy density in dark radiation is roughly 10 to the 60 ergs per cubic megaparsec if you assume delta and F is about 0.5. And as a comparison, the typical cluster, the total luminosity that clusters typically exist, which are also on kind of megaparsec scales, so it's somewhere between 10 to the 42 to 10 to the 45 ergs per second. So you can see that, to be interesting, the conversion probability you need for an axion to photon, is going somewhere between, like 10 to the minus 20, 10 to the minus 18 per second is enough for this to be luminous compared to the cluster. And the formulae for axions converting to photons are well known. In the small mixing approximation, it's simply b squared L squared over m squared per domain. And you can evaluate this, and so this is about, for typical cluster parameters, this is about 10 to the minus 18 per second. So if you multiply this, the axion photon conversion probability of 10 to the minus 18 per second, with this, which is the energy density you would have in such a dark radiation background, you can see this actually this is nicely competitive with the amount of the luminosity you get from a cluster. So this is something, you're going to be sensitive to. Okay, so in fact, axion to photon conversion will generate a soft X-ray luminosity of something like 10 to the 41 ergs per cubic megaparsec per second. And this is for an axion photon coupling of 10 to the 13 GeV. And this is actually extremely luminous. Because if you take where the actual constraints are on dark radiation, so say you allow delta and F be 0.5, and the direct bounds on the axion photon coupling of 10 to the 11 GeV, what you would then see is that you'll get a total luminosity of something like 10 to the 45 ergs per second, and this is actually more luminous than the entire cluster. Okay, obviously that is clearly excluded, but the point to take from this is that this is not hard to see for parameter values that are not at all excluded from other, say, particle physics experiments or cosmology experiments. And as a quick counterpart to this, this also means that if the axion coupling is at the sort of the limit, you can have an observable signal even with delta and F is 10 to the minus 4. And a general point here is that axions that are everywhere are much easier to detect than axions that must first be produced in stars or supernovae, essentially because you only need to pay once the price of the axion photon conversion rather than having to pay twice. Okay, so in fact there actually exists an excess in this wave band from galaxy clusters. So there's a long-standing, over the last 17 years, excess from galaxy clusters in the extreme ultraviolet or the soft X-rays at around 10 to the 43 ergs per second. So what's observed, this is excess emission above the low energy tail from the thermal Bremsstrahlung from the hot intracluster medium. It's been observed by many satellites. The main ones are the EUVE satellite and ROSAT, which were sort of, which really are actually properly observing in in ultraviolet or soft X-rays. It's got enormous statistical significance, so that's not an issue. There are obviously astrophysical explanations. This success, I think, never penetrated the BSM community. These have problems. If you want to hear about the problems, they're in my backup slides, so you can ask me about them. And this is what the soft excess looks like. So here's a plot of the soft excess, the radial extent of the soft excess in coma. It's been observed out to a large radii, something like 5 megaparsecs. So this is the Rosat 0.14 to 0.28 keV band, and this is a direct plot of the excess. At the distance of coma, 1 degree is about 1.5 megaparsecs. So you can see the excess is up to about 3 degrees, which is something like close to 5 megaparsecs. Okay, these are the astrophysical explanations. But obviously what I'm proposing here is that you could generate this excess by axion photon conversion in the cluster magnetic field. I've already made the point that the necessary energy and luminosity are easy to obtain. And it's also, and because it's basically conterminous with the magnetic field, and the magnetic field in clusters extends over quite a large radius, it's consistent with the fact that this is a diffuse excess, so it's not associated to a point source, or for example, or some central strong galaxy within the cluster. Okay, so if this is true, what would you expect? Well, the main prediction is that the soft excess magnitude and morphology is fully determined by the cluster magnetic field and the electron density, and these can be measured in other ways, for example, through Faraday rotation. The spatial extent should be conterminous with the magnetic field. There should be no thermal emission lines. For example, the oxygen 7 line at around 550 electron volts associated with the excess. And the energy of the excess should be constant across clusters and vary with redshift simply as 1 plus z, as the axion's redshift. Okay, so what we're doing right now is a detailed model of the propagation through the coma magnetic field. So I'm going to show you the plots for this. These are all generated within the last week, and in some cases in the last couple of days. So the magnetic field model we use, I won't go into the details. It's the one that best fits the Faraday rotation measurements. And so this is a paper by Bonafede et al. in 2010. So what does it look like? Okay, so these are conversion plots. So this is for going from 25 electron volts to 25 keV. So what you should see is that there's for low energies, we should go back and do this again. For low energies, there's a central deficit. And for high energies, there's a central excess. So the conversion probabilities are highly sensitive to the axion energy and particularly the magnetic field profile. So the exact rate of behavior depends very sensitively on the precise model you used, and so our analysis of this is still work in process, and there's a critical energy where you have a turnover between a central deficit and a central dominance for axion to photon conversion. Okay, so now let me conclude. Okay, so dark radiation is an extension of standard cosmology. I think it's got exceptionally good theoretical motivation, and it's also got good experimental motivation, and this is a subject where the experimental information will improve on a reasonably short timescale. Its existence doesn't require much. It simply requires that the inflaton, or whatever dominates reheating, has a decay mode to a massless hidden sector. And in string models, it's generated through a modulus decay to 2 axions. And for typical modular masses, this then predicts today is the existence of a cosmic axion background, which is free-streamed from redshifts of 10 to the 12 to now, and right now has energies in the extreme ultraviolet or soft X-rays. You can observe it through axion to photon conversion in magnetic fields, and this may already be visible through the long-standing astrophysics excess in the EUV and the soft X-rays from galaxy clusters. Okay, so if you mostly move among circles of theorists or particle theorists, there's a bit of a sort of Fender-Siegel depression over the unreasonable success of the standard models of both particle physics and cosmology. So has a cosmic axion background been observed and misidentified for the last 17 years? Thank you.
Thank you very much. Okay, we have time for some quick questions first there.
Hi, Joe. Thanks for the lovely talk. Perhaps I missed something, but my understanding was in these string theory scenarios, your value of big M was generically 10 to the 16 GeV.
So it depends. So if the string scale is at the Planck scale, then the sort of intrinsic string axioms generally do have big M around 10 to the 16 GeV. If the string scale is lower than the Planck scale, then big M is often close to the string scale. And then also you can have kind of like open string axioms. So if you have an axiom which you get from basically veving a field, which is similar to a field theory axiom, then you can have M as sort of smaller as closer to 10 to the 11 or 10 to the 13 GeV. Yeah, what you said is certainly true for models where the string scale is close to the Planck scale. Yeah.
Just on the point about the recent paper on the Hubble constant with very, very small error.
Yeah.
That is based on theoretical models for Cepheids, and they use the theoretical models, which they put a very small error on the uncertainty in the theoretical models, and try and get a distance to NGC 4258. And so, it's not an observational, determination of H0. There's no new data, so you have to believe that they're modelling things correctly. And the interesting thing is that the distance modulus they get from their theory is in agreement with the old maser distance, but is not in such good agreement with the new maser distance. And I think that the analysis that I gave of an H0 of 70.5, basically, plus or minus about 3, is the right answer, for NGC 4258 as an anchor. So don't believe the 76 or the error. Okay.
Yeah. I mean, so that was why there was a question mark there, because I can't evaluate the how controlled these models are, how understood these models are, and I've kind of asked people for an informed opinion, but I haven't had someone who can actually. Well,
my opinion, whether it's informed or not, is don't use it. Don't use it.
Yeah.
Okay. Claire.
Hi. With such an energetic cosmic axion background, do you not have a problem with intergalactic and primordial magnetic fields, if they exist? Do you not get conversion of your background into photons? So
it's one of these things. Okay, so obviously you don't know what the intergalactic magnetic fields are. If you put basically nanogauss coherent over a megaparsec, you get kind of interesting values, which are sort of something like, roughly 10% of the diffuse soft X-ray background. So you're in interesting parameter regimes if you assume nanogauss coherent over a megaparsec. But obviously that's just a guess as to what the intergalactic magnetic fields are.
Okay, but it's not so large that we would have.
No, it's not.
Okay, very, very last one.
Okay. As far as I understood, the relativistic axions you consider have nothing to do with oscillating coherent condensate axions that can be the CDM, right? What I want to ask, is it possible to reconcile the two? Is it possible to consider that your relativistic axions are just excited states on top of this condensate?
So yes, for the first 4 parts of the talk. The last part of the talk about trying to interpret the cluster soft XS in terms of this, you can't use the QCD axion, and the reason for this is you basically require that the effective photon mass in the cluster is less than about 10 to the minus 12 electron volts. So and that's the difference between the photon and the axion mass, which is relevant there. So if you have a QCD axion with a mass is around 10 to the minus 6 electron volts, then the conversion and analysed in the last part doesn't work. Up to that point, you can.
Okay, thank you. Okay, so let's break for coffee and thank Joe again for the nice time.